done in much more intuitive way back then. Okay, and then the second lecture, which will also take place today, is trying to talk a little bit abstractly about what is the telecommunication system, basically how we can model the telecommunication, what is needed, why, and most importantly, we'll also talk about modulations. This is actually an interesting concept which I wanted to start at quite at the beginning, simply because if you go to the laboratories, I would say more than half of the exercises will deal with some sort of modulation. So it's actually important to understand the concept as early as possible, so that it will be easier later on to do the laboratories. Okay. Then in the next lecture, we will talk a little bit about the coding and multiple access techniques. Well, coding is basically how we transform information that's being transmitted in order to minimize error, okay, or minimize impact of noise to our telecommunication system. And multiple access techniques, this is probably second most important or more cornerstone concept that we'll be introducing here. This got to do with multiple users sharing the same telecommunication channel. So as you might imagine, you have the mobile phones with multiple people using the same operator, the same bandwidth, and yet you can still have multiple hundreds different phone calls being made from the same area without overlapping. And this is possible basically based to the multiple access technique. So it's basically a way to distinguish between different information, different modulated signals. Then we move on to the basic information theory, signals in time and frequency domain. I believe, well, signal time and frequency domains you probably already had covered by different modules, so that should be a little bit more as a repetition. Communication channels, so we'll talk a little bit about the channel over which the communication occurs, regardless actually whether this is whether this is like electromagnetic waves, so radio, light in the optical fiber, or some pulses in copper wire. They actually all can be modeled by quite a similar thing, which is generally good news for us, right? Because that means we can have some generalizable knowledge. So that's more theoretical part, I would say. And from lecture 6, we'll try to move on to look at more practical aspects. So we'll be looking at different radio systems, what is interference and noise, and how we can deal with that. Then in lecture 7, we speak about antennas and link budgets. So this is basically how to make sure you transmit signal of sufficient power to get the message across certain distance or certain length. We'll talk about radio propagation. This is also quite a relevant topic today. So I believe, well, maybe not that often, but still every now and then, you might work your talking over your mobile, for example, or downloading some content. And you will see that there is like a corner or the street where suddenly your coverage deteriorated, or your call, well, maybe not drops, but the quality observably deteriorates. And then when you move on the other side of the street, then it's no problem. You can again get the full coverage, full speed of your internet on the mobile. And this is exactly due to issues with radio propagation, right? So basically, we will see that it's not as easy with the link budget as it seems, and we discussed some reflected signals that can, well, improve and deteriorate. It can actually work both ways, your signals. Lecture one, we moved more to the optical fibers and waveguides. I hope more or less, well, I believe you all know what optical fiber is. They are quite popular those days. Waveguides are pretty much similar concept, however, at lower frequencies. So they are typically used at at radio waves, microwaves, and you can see it, simplifying a little bit, simply as a metallic or conducting pipe within which your electromagnetic waves propagates. Conceptually, they are quite similar to the optical fibers. However, in details, they differ quite a bit. And then we move on to some more cellular networks or mobile networks to see a little bit how they work, and basically the concept of frequency sharing and how it is, passive. Well, basically where the name cellular network comes from. So what is a cell, and how it can work to operate efficiently. We talk a bit about satellite networks. There is also a talk it was actually not done in the previous year, but we thought actually it might be quite interesting for you, or if since you're electronics. So high frequency circuits. So we actually might move it a little bit earlier, depending on how the lecture progresses. So by high frequency circuits, those are basically the type of electronic circuits that are used in modulation to get practically done all the features that we discussed with modulation, and they are typically what's called nonlinear circuits. So you should know more or less by now that nonlinear circuits are a bit more complicated, so you cannot model them just by simple capacitor and an inductor and resistance by RLC components. However, they are very useful and necessary, especially in the context of radio communication. And the last lecture would be some wireless networks. And basically, I wanted to talk also a little bit radio signals in proximity of human body. So this is also a little bit motivated by recently there were quite a lot of fake news about 5G, I don't know, spreading coronavirus, whatever. So well, okay, the coronavirus, that's of course totally absurd, but they were like lesser claims about, well, understandably, people were of course worried about impact of the radio signals, and especially 5G on their health. So I believe it's actually useful to get better understanding of how this works, how radio waves interact with human body, and more importantly, what are actually standards and measures undertaken to protect us from harmful behavior, right? So basically, how does it work? And then I would like to finish, of course, with revision. So that we plan to be directly before the final test. And well, this is basically, of course, you cannot squeeze all 14 hours into one, but the idea is kind of to highlight what I believe are most important issues, and hopefully have kind of a discussions on the topics you struggled or you found a little bit problematic or interesting. Okay, so again, any questions so far, or can we progress with the technical content? So okay, I hear nothing, so let's begin. One unfortunately side note, so I don't really see here the chat. So basically, at any time of the lecture, you can stop me and ask your questions or raise a hand if you wish. Okay, so basically the rule is that, if you don't understand something or struggled, you shouldn't be shy. And if you have problems with something, it's more than likely that other people have exactly the same problem. They're just maybe too shy to ask. Okay, so please do feel to interrupt me and ask questions. And obviously it worked better with live lecture, but I will try also to make a pause or ask some questions just to make sure we're on the same page. Right. So basically, if you think about the name telecommunication and the etymology, quoting Wikipedia, it's just tele and comunicare, which it's a bit unlikely connection of the Greek word and the French word. And although it was quite late in 1904, it can basically mean anything, any form of transmitting information over some distance. That's hopefully quite intuitive. And obviously, that's not a new thing, right? There have been some very old attempts to transmit information, either by transmitting sound, like we can see here with the drums, or by fireplace smoke signals. Now this is like one of the example of the drums that were used to transmit communication. And basically, what's happening here is that depending on the place where you hit the drum, it will generate a different frequency or basically different tone, right? And that, of course, can be used if you agreed upfront with your receiver what each sequence of tones means. Sorry, you can actually transmit some information and transmit some communication. Now, even though here we actually use an acoustic waves, this is actually something that can be called as a first way of frequency modulation. Okay, so typically nowadays when we talk about, we would probably use like electric pulses or radio waves, but basically by changing the frequency or changing the frequency of a sign function that we are transmitting, we can encode information in pretty much the same way as in these drums in acoustic technology. The advancements, of course, with modern electronic, we can switch and do it at much faster pace than by hitting with the drum. However, the core principle is not actually that far off, right? So basically, you transmit a signal, and you change the frequency of the signal to embed some meaning into it. Okay. And actually, if you want, you can look how it sounds over here. Okay. Well, another approach actually are smoke signals that was quite widely used in the Westerns, right? So again, the same. You have a smoke or a fireplace, and sorry. And as you can see here, you basically use the blanket to form the shape of the smoke, or to implement certain shape of the smoke, or certain continuity, right? And this is, of course, again, some form of optical communication. However, again, this movement of the blanket, so the covering and uncovering of smoke, this is again an early form of modulation, right? So obviously, what's important here that if you just have a smoke somewhere, it's constant. It actually allows you to transmit only single bit of information, okay? Because either there is a smoke and you can see it, or there's no smoke and you can see it. That's apparently single beat, right? However, if you add this modulation over here to interrupt the smoke and shape it into certain form, you can actually transmit much more information by altering altering this mode. And this is again something that is simply a modulation, and we'll be talking quite a lot about it. So yeah, so this is actually not a new concept, although of course now we can do it extremely more efficiently. Another quite interesting example is from ancient Greece. So it was basically invented in the 4th year before Christ, and according to some record, it was used during the Punic Wars, so for communication. So basically, how it works? Well, you can see here some coded signal or some messages, and here you have a buoyant device. So it's basically a buoy, which if you add water, it will push your message upwards. If you remove the water, it would lower it down. So right, so basically, yeah, here's the water tank. Here is a tap for removing water, and by making that upper or lower, somebody on the other island could see what are you trying to communicate. Okay. Now, obviously, the problem here is that you have a very slow communication because adjusting the water level takes some time, and also you can communicate only as much information as you got precoded over here. So that's again not very efficient comparing to modern standards. Another way is so how this works in the practice is that basically the transmitter, so the one side that is wants to transmit the message over island, they would first light a torch, okay, to indicate that, okay, guys, there is a torch, we want to talk to you. Then in the second step, the water level is adjusted, so you transmit the information. Then on the receiver side, they would adjust the water level, right? So they would basically lower or upper their own marking to match those of the transmitter. And then they would lower the torch to indicate, the water level is adjusted to the intended level. So as you can see, apart from the huge inefficient water tank, they would use also a torch. And again, why they bother with that? I mean, why this was actually needed, right? And again, thinking about this with the modern knowledge of telecommunication system, there are few things that should be quite obvious, right? That because the water level move continuously, you actually never know which one is just some transient value and which one is really the information that you want to transmit. So we have here kind of a synchronization problem, right? And in modern terms, basically, we would describe this with this terminology, right? So first of all, when one side light the torch to indicate they hello guys, want to talk with you, this is what's nowadays called handshake, right? And again, a similar thing would happen when you dial a number on your mobile phone or start I don't know, browsing some data. There will be actually communication between your mobile phone and the base station, which basically says, okay, look, I have something to transmit. Can you please allocate a certain time slot or certain resources so that I can do it, right? And again, that's the thing. Well, then Step two, this is of course this process of modulation or of communication that we're talking. So we just adjust the water level until the correct information is transmitted, and simultaneously the receiver adjusts the water level, right? So this is again something we will be talking later on in modern telecommunication systems. So this is basically confirmation of corrected reception, right? So at the end of the day, you don't want just transmit things and hope to the best that they will be correctly interpreted by the receiver. You want actually embed some form of a mechanism, that you can say, okay, yes, I know the guy get it. Now I can move on to the next messages, right? So basically, this is like a form of the confirmation. And then again, when they lower the torch, again, this is synchronization, right? To say, okay, this is our fixed state. This is the thing we want to communicate. And again, like a synchronization is also very important in modern communication system, right? So basically, the idea is that with synchronization, that the receiver interprets really the value that we want to transmit or communicate with them, and not some interim value or there's no misinterpretation. Okay, so this is basically some telecommunication protocols in a nutshell. Okay. Well, moving onwards to 18th century, I think there was quite an extensive system of what was called optical telegraph, which started in 1792. So basically it was a network of stations with different shape of the arms, and again similar to the visual interpretation. This allowed to by observing neighboring tower or neighboring station, you could see, you could transmit information. And basically back on the times, that was kind of a revolution. The reason being that contrary with the torch, when you have this, limited number of messages, simply with this system, you got much more degrees of freedom because you have some additional arms that you can adjust. So it basically means that you can communicate more information at once. Okay, so in the ancient Greek, you have probably 4 or 5 different water levels, and so you could choose out of 5 options. Whereas here you have like a full alphabet, and also the digits in one go, in one symbol. Okay, and this is something that again, the principle doesn't change, right? Both in ancient Greek and with this optical telegraph, the principle was the same, right? We observe what's happening visually, what's happening at the other station. However, by using more symbols, having more degrees of freedom, you can actually transmit, more information at once. Okay, so you didn't need to wait it, let's say, 5 hours and go through all the water levels. You can have more degrees. So again, looking from the information theory and telecommunication system, this is something what we would call an alphabet. Okay, and an alphabet, it doesn't really mean that there is like a real alphabet and digit, but typically in telecommunication system, by alphabet, we mean a closed set of symbols within which you can choose. Okay, so also actually in the case of the water level, we see here there are, I think, 7 different water levels marked. Okay, so in the case of this device, our alphabet consists of 7 different water levels, right? Whereas here, we have, I believe, there are shown 36. I'm not sure actually if this covers the full set, right? So we have like 7 symbols in our alphabet compared to 36 in our alphabet. And what's basically happening here is that when you have more letters in the alphabet, you can communicate much faster, okay? Because you can communicate much more bit in one go, in one what's called symbol, right? Because by transmitting one of those symbols, you can actually narrow down your information quite precisely, okay? I hope this is more or less intuitively understandable to you. So again, the communication can go faster and faster. And we are assuming here not even by switching between symbol more frequently, which was apparently also the case here, right? But even if you have the same symbol rate, by having bigger alphabet, bigger set of letters, bigger set of symbols here, only this will provide you more information, more bits per second that you can transmit. Okay. Of course, there's no free lunch, and for this increased speed of communication, there's also a price that you pay, right? And it comes with the fact that if you have, 5 different levels, as with the water tower, 7 different levels, as with the water tower, it's typically much more unlikely that you will make a mistake, right? Because there are just only 7, so picking 1 out of 7, it's much more distinguishable. Whereas, of course, in that case, you can see that small details of the semaphore arms can make a difference, right? So basically, and this is basically the price that you normally pay, that you have to distinguish more precisely between different symbols. Now, obviously, this was not a problem in 18th century time because they had already binoculars and some optical devices, which were not present in ancient times. Okay, so however, it's more about the principle, right? That when you communicate more symbols, you can transmit in general more information, but you are also more prone to noise, more prone to error, and more prone to noise. Okay. And this principle, as we'll see later with some IQ modulations, it is actually the principle which still holds until today. Okay, and just to finalize on the semaphore telegraph. Yes.
I have a question about this alphabet. Why would there be a 10 but not a 0?
That's a good question, actually. To be honest, I'm not sure. Probably you should ask Cloud Shop how they design. What I simply believe is that this is not a full set, so probably there must be 0 somewhere. But yeah, you're right. Obviously, 0 would make much more sense here. Sorry, the answer is I don't really know. I think it might be simply, just a subset of all possible symbols, for visualization how it works. So apparently that's what I would expect. Okay. Okay. Great. So, right, and this is just to give you some visualization on, the extent of the telegraph network that was operated back in the time. So it consists of 533 relay stations. And overall, the message from the other side of France could actually arrive within like a few minutes, which well, back in the days compared to, riders going few days, that was actually very, very quick. So yeah, just as a comparison, so apparently Napoleon quite liked the system. And just as a benchmark, so after the Battle of Austerlitz, which was not covered by the semaphore telegraph network, it took actually 10 days for the news to arrive to Paris. Okay, so you can imagine 10 days comparing to few minutes. That's a huge advantage of the system back in the days. Okay, lastly, and this is something, this is actually last device, or last historical device I wanted to point out. So this is basically like a heliograph, and surprisingly, it was used even in the 20th century. So just quite recently by the military. Well, the advantage probably was extreme simplicity. So you just have device with a tilting mirror, which reflects sunbeam, and by tilting the mirror, you can generate sequence of pulses. Okay, so again, as you can see in blue, speaking about the theory of telecommunication, again, that can be seen as pulse modulation of optical signals. Again, primitive and very inefficient, right? However, the concept is still there. And well, as you can see, it was pretty much also dating back to the ancient times. However, the proper device, as you can see it here, was discovered in 1869, and again, it was very popular in 19th century, mainly due to its simplicity. Okay, so the range was up to 45 kilometers. However, again, you could use telescopes to as a receiver to increase it up to even 200K. So thinking about the system, or actually maybe you can kind of help me with that. So basically thinking about such a heliograph, when we have like the transmitter using pulses with reflected mirror and the receiver somewhere else trying to receive that. What would you expect could be the pros and cons of such a system? So can anybody maybe speak up? Well, okay, so
someone could break a mirror.
Yes, that's this is actually true. Although, yeah, well, usually the mirror would be kind of attended, right? But okay, it applies pretty much, to any radio system, right? You can also break the mobile phone, but yeah,
everyone could see the signals from the other side.
Yes, exactly. That's what. So security of your communication. That's actually one of the topics that is quite relevant. Well, and anything else? I mean, the most
maybe some dependency on the weather.
Exactly, right. Not only actually weather, right, but so yeah, of course, weather is one thing, but also day and night, right? So obviously, if you're just using passive mirror without any active signal, you cannot do the same when there is a night. That's good. Right. Any other ideas or?
What about any kind of noises? Like, I mean, for example, light pollution from another torch or something.
Yes, exactly. This is actually another good point. We'll be actually talking quite a lot about that in I mean, well, not in the heliograph, but in a similar case of noise pollution. Yes, indeed, right. I mean, you can see some blinks or whatever, and have problems with interpreting the signal. That's very good, actually. Anything else, maybe on the positive side?
I don't know how accurate it was. I don't know how accurate it was, but I guess you need to aim it.
Yes. So basically, the aiming and security, right? Those are the two aspects which are kind of trade-off here, right? So basically, the more you need to aim, the less likely it is somebody will intercept your signal, right? But on the other hand, so basically you can narrow your beam, right, to have better security. But then you need to be more precise with your aiming, right? And vice versa. You can increase somehow the size of your beam, right? And then you are more flexible with aiming, but then again, there are more people that can intercept. So the security is more of a concern. So those are kind of the two aspects which are actually a bit contradictory. Okay. So yeah, as you basically mentioned, day only and weather is dependent. Well, just to say something positive, this is portable and no power, which is basically no passive. So okay, you can indeed break the mirror, and that did happen. However, in general, it was still more reliable than some of the primitive radio equipment, which required battery, required back in the time, quite large antenna, and were basically heavy. So that's the thing. And again, the device is very simple. Also, what was happening, I actually it didn't show up. It was very easy to be incorporated into network, right? So what we mean by that is, of course, you want to communicate between the two devices, but overall, you prefer actually to build a network of multiple links connected with each other, right? So it's similar as with the semaphore system in France that I showed you earlier. I mean, there's no point if just the two towers can communicate between each other. Great, that's fine, right? But if you have another device, and another device, that's when you can get quite a big synergy effect, actually, right? And when you can have much better actually telecommunication. And that was partially the case here, right? So you should basically you could use, 3 or 4 of the devices that surround you, communicating and transmitting information into different directions. Now, some discussion we already had. So yeah, so this was already mentioned, the issue of security, and somebody could see the signal. A solution to that could be actually that you use some tube in order to narrow the beamwidth, right? So basically, the idea here would be to be, more selective with your communication, so that if it covers narrower range, it's of course less likely that enemy or in that case actually enemy, because there were military devices, would intercept your communication. Then there's that was also mentioned by you, there's the issue of coding. So basically, how to interpret flashes, right? If you see just a single flash, whether this is really the intention of the transmitter to, just communicate single flash, or was it just, sun that passed, or whatever, some random effect of noise, or maybe just the, guy made a mistake and he has a shaky hand because he's doing this for the first time, or I know there was a big party the previous night in the camp, and he cannot be as precise as they used to be. Okay, and again, that was, how do you think it would work if you're communicating with a mobile target here? Because this is also another aspect, right? It's a bit different when you have a stationary receiver, and it will work totally different when it's mobile. So how do you think? I believe in, yeah. So what do you think will be important here, or any challenges, any issues?
You need some tracking system.
Yeah, in a way, you need tracking system, right? Also, in the previous, there were mention of the aiming, right? So obviously, if you have a mobile target, the aiming would be much more challenging, right? Much more difficult. So you need to be much more precise with that. Yeah. So and back in the times, it was actually quite an issue, especially when we're communicating with the ships, right? So because apparently ship which was rolling on the waves was, you could see basically like additional flashes, not because there was no intentional flash, but just because of the roll of the ship. And And then, of course, one of the solutions for that would be to use lenses to, as I mentioned, widen the beam width, right? So basically, they would like spread your optical signal towards wider angle, so that it could, also cover moving objects. So, as mentioned, there are always some trade-offs, and depending on how you want to use your your system. All right. So with that quick historical overview, we now move to how we can. The question now is how we can describe it in a systematic level as more body of knowledge. So just maybe what I propose is, so we have now 5:12. So if this is okay for everybody, I propose we go until 12:30 with the lecture. And then we can make like a 15 minutes of break and continue with the second part. Is that okay for everybody?
Yes, it's okay.
Yes, okay.
For me at least.
Yeah, okay. Well, I hear no protest, so I guess that's the majority. Okay. All right. So again, the telecommunication system, the point is to transmit information from one location to another. And okay, firstly, to transmit information, you need to have that information, right? So you need well, the generation of information is the first step. And from our point of view in the telecommunication, we don't really care that much what that information is, right? So it can be, some idea, it can be some measurement, it can be voice, it can be data. It doesn't really matter what it is. And also we don't care about interpretation of that information, right? So most likely, of course, you are transmitting that information so that somebody can make a use and it can inform some decisions or have some impact. However, within the telecommunication system, we don't care about what is done with that information. Right? This is again some abstract system. So basically, then we have to describe that information. Okay, because well, obviously, you cannot. If you have some thoughts, you need to first describe it or verbalize it. You cannot transmit abstract concept anywhere really. Okay, and what is important to understand that even at this description of this information, we have quite a limited precision, right? So of course we try to narrow it down to be as precise as possible, assuming that's required, but it's pretty much never 100% of the idea that we have at the very beginning. Okay. Then once you have this formalized or described information, you need some sort of a coding of the symbol. So this is different from the first block because when we speak about coding, we already think about the channel over which we'll be doing that transmission. Okay, so sorry. So for example, the description is I don't know, a file in your computer program, right? But in order to send that file, you typically need to code it in a certain way that it will basically not get corrupted when transmitting over channel, right? And yeah, while doing this coding, then of course we do the transmission, and then on the receiver side we actually go through all the steps in the reverse direction. So we go for decoding and extraction first of the symbols. And then from that symbols, we can get the transmit the symbols into the information for further use. And then again, the receiver can do whatever they want with that information. That's other story basically. Okay. So to put that into the block, there's the information source, and those are the blocks that we have been discussing, right? So we have the information, which again is just the data. And then we have a sender, which basically formats and prepares the information so that it can be transmitted through some physical channel. Okay, what's important, we really need some medium, some sort of a channel over which we can transmit, right? So in the context of the heliograph, in the context of the optical, in the context of the water signaling, that would be optical communication, effectively some visual or optical information. In the case of the drums, that would be acoustic waves, right? That are our channel. But of course, there's much more, right? Nowadays, radio waves are the most commonly used channel. A fiber cable or a copper cable, that would be our channel. And by channel, it's again a little bit abstract process in the sense that we also want to see some processes, what's happening with our signal in there, right? So typically, the channel will see addition of a noise. However, again, this is pretty much generic, right? So depending of which channel we use, who is the sender, who is the receiver, the details will change. However, the general framework will still be the same. Now, okay. Now, breaking, and then this area highlighted in yellow. So this is basically the part of which we call telecommunication system, right? So as I mentioned, we don't care how the information is generated. We just get it as an input. We give as output, already the information, and then, whatever is processed, that's a different story. Okay. And typically what will be the main villain in these lectures or in telecommunication system is the addition of the noise here. Okay, so I know you all probably know what the noise is more or less from the basic electronics. However, in the context of telecommunication, your noise is it's really much more significant than in your daily electronics, right? The reason is that typically in your PCB you have very small distances, and yes, you have a problem with noise. However, if you think about the telecommunication system, this is really we're thinking about transmitting over large distances, and a lot of noise can be actually gathered on such a distances. So pretty much most of what the next lecture will be is actually how to build system to be resistant to noise, okay? Or basically how to communicate what you want to the receiver, even in the presence of high noise, right? And that's basically a random process, which is source of error. And that's why we need all the blocks that you see in the next slides, okay? So basically this is sort of more detailed description of the system. So we broke down the transmitter into decoder and sender. Okay, so again, going back from the information source, decoder is what would process your information. Okay, so typically, in the computer, when you have the stream of bits 0 and 1, 0 and 1, 0 and 1, however, it's not the best way of simply transmitting the very same zeros and ones that you get from the computer into the sender, into your telecommunication system, okay? And the reason is that, as I mentioned, at the end of the day, you have the channel with the noise. And depending on the channel, you would try to do some coding, which will be intended to detect possible errors and also to make your signal later on as immune as possible to occurrence of that noise, right? So firstly, of course, want to make the signal immune, prevent it. Secondly, if there are any errors, we actually want to be able to detect them and know, okay, we received something, right? But we know that there are like 5 bits mistaken, right? So we ask for retransmission. Okay. Then when we have the sender, that is the part which transmits the signal. So basically, it is the process of modulation, which would change some physical property in order to encode your information within. Okay. And there is a quite an important distinction over here. So basically, when we speak about the information, we typically use the form data or a message, which I believe you're all well familiar with what the data is. However, when we already start processing our signal, our information actually, and preparing it for transmission, we will be talking about the signal. Okay, so the clear distinction here is that the data is just like rows of 0 and 1s. Let's call it this way. Whereas with your signal, you already think about some physical property that will be later on modulated to transmit that information, right? So that would be, for instance, some voltage levels or some amplitude and phases of your radio waves. And again, similarly, what's on the transmitter need to be repeated at the receiver in order to unwrap all that information. So I think to visualize the difference and what's the point here, I got this kind of slide here, right? So this is pretty much what we are doing right now. So there's a lecturer which like myself, and in my head I got some information, right? So this is basically the abstract idea of telecommunication system, right? Which I try to convey from my brain into your brains. Let's put it this way, right? So then there's this vague information of what is information source, and first those information is coded, right? And this is the coding actually is done in the brain, to be precise, in what's called the broadcast area. So that's the part of the brain responsible for formulation of speech, right? And there is a transition from the abstract information somewhere in my head to really some words, basically, right? So I put in my head some words, how I can explain that to you in the best possible way, okay? Then those information is executed, right? So I use speech, so I put my mouth and other parts into motion to basically generate sound waves and transmit this information. And okay, and then we have a channel which are acoustic waves. Well, again, nowadays, of course, we have the online lecture. However, thinking in the classroom context, this speech, this wave will simply propagate through the classroom, and then and there will be also some noise added, right? So the noise can have multiple forms. I know somebody can be talking in the last row. There can be, I don't know, some drilling in the next room, or basically anything that will add some additional signal on top of my speech, which would make it less understandable. All right, and then it hits first your ears, right? So the ears can be seen here as the receiver. So basically just accepting that information, trying to basically demodulate the movement or the vibrations of the acoustic waves into specific sounds, right? In specific sounds. And then, of course, you have also a decoder, which in the case of listening is called Wernicke's area. That's, again, different part of human brain. And that would serve as, decoding this information from this acoustic information of different sounds, interpret them into words, right? And then again, based on those words that you've listened first here and then understood here, you will try to recreate that information and form some idea about what the telecommunication systems can be in your own brain, right? To reconstruct that information. But of course, as you can imagine, usually this is not a simple way, right? So it's not really guaranteed that what I'm have in my head and trying to transmit that, what's at the end happening here is, of course, never the same as I transmit, as what I'm trying to convey to you. And also there are some ways of kind of reception so that I as a transmitter, need also some back information whether the communication was successful, right? Whether the information was accepted and transmitted successfully to the user. And I'm not sure if you know what I have in mind or what serves as this sort of a confirmation signal.
The responses, like yes or something?
Yes, this is actually one way, of course, and that's why I'm trying, trying to...
The thing that doesn't exist on Microsoft Teams in e-learning.
Yeah, but also in the big picture, well, again, a part of trying to ask you questions and so on. But of course, the ultimate way of confirmation whether the information was received is actually the exam at the end of the module. Okay, so that basically is the final confirmation received for me whether the information received or not. Okay, so again, as you see, this can be put into the quite a lot of the framework can be put into work in many different contexts. Okay, so here again, going back into the same block diagram, using again more precise terminology. So as you can see here, the coder was split into the source coding and channel coding. And this is, again, one more important distinction that is supposed to be mentioned here. So typically with the, even both are called coders, they have totally different purpose, okay? So typically with the source coding, we are trying to process the information in a way to extract the key components out of that information. Okay, so typically when we speak about the source coding, we are taking our information and we are trying to basically strip it from unnecessary elements, right? Because the more elements you need to transmit, the less efficient you are, okay? And then once we strip it from all unnecessary information, we move it to what's called channel coder, where we add some more information, some unnecessary information, okay? So seemingly, actually, those two blocks are doing the contradictory job, or they're like one is stripping down the information, whereas the other is actually adding some redundancy, some extra bits and information. Now, do you have an idea actually why is that, or why this might be useful in this context?
So the receiver can check if information is correct?
Yes.
Fix it.
Yes, pretty much yes, right? So when we have the channel coder, we add some information, right? But it's not any information. This is additional information which is tailored in order to make it more robust, given the channel that we are using. Okay, so it's like, first we are again stripping down the amount of information to send only that's what's really necessary. However, once we got this necessary, so for an example of the source coding could be something similar to zipping, right, or a compression. That's one of the examples. And once we have this reduced amount of information, we add some more to combat the noise, to combat the channel, but in a smart way, right? So it's really engineered and designed, not any bits. Then, great. Sorry, I just noticed, of course, obvious mistake in this slide. Then, of course, there is the modulator, and typically by modulation we mean covering the output of the channel coder into some physical medium. Okay, so we basically have we need some physical parameter that is going from A to B that encodes our information, right? I mean, obviously we cannot send zeros and ones over any distance, or bits over a certain distance, right? We always need to use something that is physical, that is existing in the real world, and just alter that to which would serve as embedding that information. Okay, and then of course we have the channel and the noise, and here's of course obvious copy-paste mistake. Obviously the arrows should go the opposite direction, and it should be not modulator but demodulator, channel decoder, and channel decoder, source decoder, sorry. Right, so again, what we do at the transmitter need to be undone at the receiver. Typically, actually, using and unwrapping your information at the receiver is much more complicated than transmitting it, but conceptually the blocks are equivalent. Okay. So this is basically to frame all of the things that I was mentioning here. So firstly, in the source code, we remove any redundant information. And again, compression is one of the things. Also, in some sense, we would embed, if we do any encryption, that's also the component that would be considered here in the source coding. So I know technically encryption is not necessarily reducing the amount of information, but still that's officially labeled into this block. Then in the channel coder, we add redundant information to prevent distortion. And then in the modulator, we altered some physical quantity. So for example, this would be, let's say, changes in the light intensity of light pulses in optical fiber, or change of a frequency in case of radio signals if we're using frequency modulation. Okay, right. So yes. Mm-hmm.
I know that in case of HDMI, it's before the data is sent, it's trying to balance out number of ones and zeros. So this would be what on this diagram?
Sorry, can you repeat once?
In HDMI, this video signal, there's a process where it's trying to balance out the number of ones and zeros. So which block is that?
So this is a good question. I have to say, I believe, so this would be basic, I believe that would be more of a channel coding in that case. So, so I presume there might be some feature in the standard that you typically might not like to have dominating ones or dominating zeros due to some physical properties. So I have to admit I'm not an expert in HDMI standard. However, again, I would expect it to be the part of the channel coding here, right? So this basically depends on, of course, on much on the context, or why is it done? And I would expect this equalization is again done to avoid to avoid some sort of errors or so.
I think it's to avoid DC current in one direction.
Okay, yes, fair enough. Okay, so so this will be actually kind of a combination of okay, this is a bit more complicated then, because it's also got to do in that case, right, with the electronic construction of the transmitter and receiver, right? But still, I would label that actually as the part of the channel coder, okay? Because at the end of the day, you are, you're removing the DC constant in order to make your signal easier to interpret or receive by the receiver, right? However, however, this is basically not a typical case. But yeah, I would say this is part of channel coding. Okay. Okay. So yeah, what I want. Right. So, are there any more questions here at that stage?
I just have a little bit unrelated question, but still, will the slides be uploaded on ePortal or somewhere?
Yes, they will. So basically,
okay, great.
I believe simply, putting them on in the Microsoft Teams folder. So in the same folder that we are using for the lectures, just that you have everything in one place. Just of course, what I would ask from you is that those slides would be, of course, for your private use. Okay, so just please don't distribute them into the wild internet or anything like that. Okay.
Of course, thank you.
Yes. Right. So, are there any more questions? Okay. Well, if not, then I propose to make a 15-minute break here. So, or maybe even, so yeah, I propose let's meet 1:45, okay, and then we will have the second part of the lecture. Okay. So, yeah, thank you. So thank you very much for. Yeah. Yeah, that's true. Sorry, I just noticed the
when
comment
will
about
this lecture will end? Sorry.
Sorry?
When this lecture will end?
Right.
What time?
So basically, we were having like a 4 times 45-minute lectures because we are making up for the missed lecture. So I think if we start 1:45, that should be 1.5 from well, approximately 1.5. So I would say 2:15, assuming everything goes goes on time. So I think we're a little bit ahead of schedule right now.
Okay, all right, got it.
Okay, so
Thank you.
no worries. Okay, so I see you in 10 minutes right now, and okay. So, sorry, I just it's okay. So now we will continue on with discussing the coder and the channel again. Just start sharing the screen first. Okay. So again, can you hear me and can you see the slides now?
Yes, we can see.
Brilliant. Okay, so that's when you start with discussing the different elements, and now we of course want to go into more details and break that into different parts. So we'll start with the coder. So as we already discussed, right, coding is well, to define the process formally, it's a way of changing the representation of a given signal, which is more suitable for the intended purpose, right? So over here, actually, I got an just example of a Morse code. So again, thinking, back in the times when the telegraph was invented, well, of course, humans or people were using alphabet for centuries, and but suddenly they needed to communicate over larger distance, but using wire and electric currents over a wire, right? So obviously you cannot send the letters over that wire. So a special code was invented with dots and dashes, right? But basically those dots and dashes meant, short voltage pulse and longer volt or current pulse when transmitting in a sequence, right? And this was basically exactly, the purpose and the form of, transmitting that information, right? That it was, much more robust and much more efficient just to transmit short and long pulses than letters, and that was the idea of the code. And then a single element of a code is called a symbol, right? So basically, each of those, so dot and dash, that's a symbol which corresponds to the letter A, which, well, itself is actually different symbol, but that's okay. Then dash dot dot dot. This is again one symbol. Okay, so so basically, yeah, a symbol has one meaning by itself, right? It's not that a dash is one symbol, dot is another, and so on. And then when you use the sequence of symbols, this is what is called a code word. Okay, so yeah, that's to get the nomenclature wrong. Now, nowadays, what is very commonly used is called the block codes, and this is again done in the context of channel coding. So, well, how does it work? Basically, the name reveals quite a lot. So we have a constantly flowing stream of information, and basically this information is divided into blocks of equal length. So let's say each block contains k symbols or k k bits or whatever it is. And then the k long block is converted into longer and long blocks. So we are basically adding bits here. So again, this is the classical example of the the channel coding. Okay, and then those other bits, that's the thing which allows for redundancy. Okay, so this is the part that we get control over errors that may occur in the channel. So at the end, we are transmitting more bits, more information, but because it's more robust overall, we got gain in the form that we don't need to repeat the same information twice, and we can be certain that the information received as intended. Now, obviously, there is some trades-off here. So if we add too many bits into the code, then well, we basically jeopardize the source coding, right? So it might be that that if you add too many bits, you put more burden on your communication channel, and that might not contribute to anything good. So even here we need to look for a certain trade-off, because you want to add as many bits which will get you high probability of getting without errors, but not too much, because then it's still a redundancy, right? Those are unnecessary bits, right? So you're basically looking for some sort of a optimum, and when you just avoid it, so don't add any bits, then again, based on your channel, you might see significant loss of information. So the net gain is again not negative, because you might need to repeat the information and so on, right? So this is like the main question when you are looking into different codes. Okay, so what amount of redundancy is sufficient enough to get your message across with high degree of probability, because you always operate here with probability. You very rarely are like 100% sure. So 99, 98%, that's actually good enough for us. But so what's the amount of redundancy that does the job, but is not too long, does not extend your block too long, so that you need to use more redundant than meaningful bits, or more redundant information than meaningful information. Okay. Now, one of the examples here is the 4B 5B code. So it basically turns 4-bit sequence into 5-bit sequence. So obviously the input is 4 bits, and the output consists of 5 bits. Now, it's to make the system robust, there are some different operations here. So how this code was designed is, firstly, each code word contains at least 2 ones. Okay, and you can see that there is no code word with less than 2 ones. Then there's no sequence of code words that can have more than 3 consecutive zeros. And then it prevents occurrence of long sequences with only zeros, right? So as I mentioned, I can produce HDMA standard from the top of my head, but actually from the description, this looks as something quite similar to what might have happening in the process that you described. So why those aspects are important in this context, right? So firstly, the idea here of the code is to avoid long sequences of 0. And the reason behind that might be that if you have a very long, if you're encoding 0 as let's say no voltage or 0 voltage, and then you encode 1 as some voltage or some pulse, you know, naturally doesn't want to have very long sequence of zeros, because then, you know, if your wire breaks, you cannot actually distinguish meaningful information from simply, you know, broken circuits, right? That's not really a good thing. So that's why the bits are rearranged and transformed in order to you know, to prevent this occurrence of low sequences when the voltage would be low or negligible. Okay, and then, well, yeah. Okay. So going into like some again basic code. So, you know, this is the most simple what we can do, right? So we have some zeros and ones here at the top, and we simply encode 0 as no impulse and 1 as a positive impulse. And again, this is of course very straightforward, right? Very simple. So, you know, the cost of the electronic implementing this would be typically very low, right? But can you see why this is not the best idea? Or what are the drawbacks basically of this coding? I think one possible side effect I already mentioned with the previous slide.
I mean, I don't think that's the one you're looking for, but this one cannot detect, I think, changes in bit flips.
Yes. So yes, obviously there's no error. You're right. That's not exactly what I was looking for, but that's of course correct, right? So there is no error correction yet embedded into that. That's true. I was more looking at the very basic, at more, you know, physical layer here, right? So right. So first of all, when you know, do the design, like it's the same problem as I expressed with the previous slide, and that when you have, you know, consecutive zeros, you know, you don't really know whether you're transmitting no information or you're transmitting some information, right? Because in theory, you might have very long sequence of zero, right? Of zeros, of no voltage or no impulse, and that would be still your information. And that's something that might be, you know, very difficult to detect by your receiver. Okay, so something like this would be actually much more better. So we encode, you know, negative impulse and positive impulse as a two signals of opposing polarization, right? And in that case, even when you have like a long sequence of zero, there is no ambiguity here. So you still know this is not some broken circuit, but a meaningful signal that you really intend to transmit those zeros. Okay. Now, what is the difference between those one? Okay, if you use as a zero as no impulse, but you use 1 as a half-long positive impulse.
Clock recover.
Sorry?
We can recover clock.
Exactly, right? So in that case, if there is misalignment or wrong synchronization between the transmitter and receiver, you know, without proper time scale, really you don't know whether, whether this is, you know, single pulse or maybe two pulses or 3 pulses, right? Again, here you have no problem, right? You know, that's the beginning and that's this is 1 pulse, this is second pulse. Again, since we use 0 as no impulse, you still run with the original problem, right? Alternatively, you can also use interchange positive and negative pulses. Why you can use this? That's a bit more tricky, actually. But so we know, of course, with this you already have the clock embedded, which is a good thing. But what is additional benefit with such coding?
Parity check.
Yes, parity check, right? And basically, parity check. It's actually partial parity check, right? Because you check for parity only the pulses containing 1, right? But basically, the parity check is the very simple and very primitive way of the channel coding, right? Of adding redundancy. Because if you look from the theoretical point, you have here actually 3 different states that you need to distinguish. So your alphabet in that context has, no voltage, positive voltage, and negative voltage. So your alphabet is from 3 letters. So theoretically, you can get tempted, to use this not as a free state transmission, and then as we mentioned earlier, that would allow you to transmit more information, right? However, in this code, you decide to sacrifice the extra capacity of your telecommunication system to get some basic error check, right? So if you get 2 positive pulses, that there is something wrong here. So this is indeed the very basic form of error detection, not yet correction, but at least you can detect when something went wrong. And also going even more complicated, right? You can have a dynamic system. So with that, you simply code as well, basically, if there is a 1, there is no change in the value of your bit. If you if it's 0, you simply change the bit. Okay, so that's a bit more fancy. Okay, one good example actually is what's called Manchester code, and that's actually quite commonly used with Internet protocol, which so the Internet protocol that's very often used at IEEE 802.3. We'll be talking also about standards and protocols probably in the next lecture here. So how does it work here? Well, basically you got this data bit stream of 1s and 0, which goes on, and then you have the clocking signal. And with this coding, you do seemingly the simplest thing you do. Right? You perform XOR operation between the data and the clock. And you end up with such a sequence of positive and negative pulses. Okay, so basically every bit you are sure that there is some change which occurs, so it avoids this problem on having 2 long sequences. You got embedded clocking signal, so you don't need to worry about clocking. But also what's important here is that also generating that is so coder and decoder, it's just pretty much one logic gate, right? Because doing XOR operation with a 2 signal from the point of view of electronic equipment, that's really very very straightforward, right? So that's simplicity, and in a simple way you avoid quite a lot of sorry, problems that you might have just by transmitting it in a different way. Okay, now modulation. Sorry, actually, are there any questions in relation to this section of the lecture? Okay. Okay, so I'm assuming there's not. So We move now to the next block, and we will revisit still coding with the looking more into different ways of error correction and detection. And now we move on to the block which is called the modulator. Okay, so basically modulation, that's again a very basic but fundamental process to I would say actually all telecommunication systems. So the idea is that you have certain physical quantity that exists, and you try to alter that physical thing in order to encode to encode some information. Okay, so now so much for the theory. So the most common what you will see here is like a high frequency sinusoidal signal. So that would be our our carrier what's called carrier signal. Okay, so this basically it can actually represent both radio signal or signal in a wire. Well, I usually actually use the example of radio signal, but this parts come partly from my background here. So basically you have like a periodic waveform and radio signal of certain frequency, let's say, I don't know, 110 megahertz, right? And this is basically the frequency of the sine function that is being transmitted as a radio. And very often actually when you look into the well, be it like a radio broadcasting, the old-fashioned FM broadcasting radio, or if you look into frequency of Wi-Fi channels around 2.4 gigahertz. So typically when there's like one value expressed in hertz, megahertz, gigahertz, whatever, that typically corresponds to the frequency of the carrier signal, right? So this is your this is the signal that you receive. Now, obviously, by receiving a signal that's not it cannot really transmit any information. I mean, well, it can one bit, right? You receive the signal or you don't. But hopefully by now you should realize this is not a good way of doing things, right? So we need basically some way of modifying that signal. And from practical point of view, typically that means our signal need to have much lower frequency than the carrier signal. Okay, so typically we would use in terms of a speech, we have a signals corresponding to kilohertz, right? And then when we modulate that to, let's say, FM radio broadcasting, we move this few kilohertz signal into the 100 megahertz, right? So this is so basically for most electronic systems, we simply shift the frequency of our original signal, what is called the baseband signal, into the into the higher frequency regime, right? And just as a side note, maybe here, what I wanted to point out is that looking again from the principle of the electronic equipment, you are shifting the frequency of your signal. So basically, in effect, you are generating signal at new frequencies that were not used previously. Okay, and this basically means, if you think from the point of view of electronic devices, this means you actually need to use nonlinear electronic components in order to perform that information, right? Because again, if you use the passive RLC components, like no matter what you do using coils, using capacitors, it won't be able to shift your frequency. You need either a diode or transistor, again, something nonlinear to make that shift. And we'll be discussing later on towards the module about this. Okay. Now, for the time being, actually, just let's focus on the on the very basics. And again, I really would like that you fully understand what is modulation and that works, because it's really like the 101 basic of telecommunication. And again, you'll be using that quite often in during the laboratories. Okay, so what we can see here is this slowly changing signal. This is what's called low frequency or baseband signal, and we assume here this is the signal which already underwent through all the source coding, channel coding, and it's ready to be sent. So now we have to modulate that. Okay, so this is the slowly changing signal, and here in the red or blue we can see the high frequency carrier signal that has already been modulated with the black baseband signal. Okay, so in the case of the red curve, we speak about AM, which is amplitude modulation. In the lower case, the blue curve, we speak about FM, so frequency modulation. Okay, so and basically, so how does it work? Well, in the red case, the amplitude modulation, we simply have our high frequency rapidly changing radio signal, and we introduce small changes of amplitude, which correspond to the changes of our original signal that we want to modulate to send across, right? And this is basically the end effect. So we still have this radio signal which is changing very, very fast, but when we kind of forget the signal and use some component like, well, even diode is not the best way of doing that, but in theory you can think about some diode bridge that would just get rid of those sine component and simply extract the amplitude of your signal. You can recover on the receiver side your original signal, and that will be basically the demodulation, right? On the frequency modulation, this is a little bit different. So you have certain one baseband, one frequency, and you modulate your original signal by changing frequency from lower or higher, okay, while still being within this higher frequency radio domain. So you can see here, right, that when there's the minimum of the original signal, the frequency is actually lower, whereas for the maximum of your signal, the frequency is higher, right? And again, you can then, on the demodulator side, you can just look at the frequency shift, and based on the frequency shift, you can translate that into your original baseband signal. Okay, so far, is this concept clear? Or are there any questions towards the concept of modulation? Or okay, I hear no questions, so either everything is clear or nothing is clear and you don't know even how to ask a question.
It seems clear, I guess.
Okay. Okay, great. So my next question actually is, again, that's actually something you will hear probably quite often in this lecture. So what can you imagine are pros and cons if you compare amplitude modulation and frequency modulation? What advantages or disadvantages you can see for both? So I can also add that historically the amplitude modulation was actually the first way of broadcasting radio signals. Okay, so anybody, how and any ideas? So thinking in terms of, well, firstly, simplicity of transmitter and receiver, thinking if you had some noise on your signal, what would be your choices with regard to those two parameters?
I think the AM signal might be like when the source signal has a low amplitude, then that parts are more susceptible to noise, when in FM they wouldn't, because the signal is like after modulation, it's the same signal strength for all amplitudes of the source. I think
yes, that's actually that's a very good remark, right? So indeed, it doesn't mean that the FM signal is immune to noise, so you can still misinterpret your communication. But this is true. Basically, if you have the lower amplitude here, you might get problem with noise, or more importantly, not each portion can be subjected the same. So this is true. Well, and any other ideas? What are pros?
With AM, you have maximal modulation depth before the distortion, about 30%. So if you want to modulate the voice, you can't put more power into AM than 30% because most goes into the carrier.
Yes, this is true. Well, in terms of power, it's true. However, you would also have certain saturation level, so to speak, in terms of frequency modulation. The difference is that, in terms of frequency, it will be limited by your range of the minimum and maximum frequency that you can use, right? Because you don't need how to say it, you cannot extend between the certain frequencies that you're allocated for your frequency modulation, right? And this typically can be also a problem, because frequency modulation to especially to get good resolution, they might require also wider bandwidth of your signal, right? Because of course, to modulate from the F min frequency to F max frequency, that's something, well, it will occupy wider portion of your bandwidth, basically. And this is a problem because nowadays, well, this could be a problem, given that nowadays we're actually using quite a lot of wireless devices, and in some portion of the bandwidth, it's really very packed, right? So you really, and there's actually a lot of research and a lot of work being done now to try to reuse the bandwidth or recycle efficiently, simply because there is not enough bandwidth, and in order to communicate, you cannot use in general, okay, we'll be talking later about the multiple access, but it's not straightforward basically to use the same bandwidth twice within the same area and region. That would cause interference and problem, right? So but the bandwidth issue is of concern here. Okay, so basically, yeah, but those are the basic of analog modulation. And those are actually the two basic concepts of amplitude and frequency modulation. Now, if you think, of course, you could do the similar with digital signals. So the only reason would be, of course, that instead of a continuous signal here, like a sine wave, you would observe, a pulsed signal, basically a digital pulse signal. However, there's also actually one very popular way of doing modulation when we move to the digital. Right? So, okay. So basically, the amplitude shift keying, this is simply a different different way for this amplitude modulation, but when applied to the digital signal, it got a little bit different name. Now, there is a thing which is called phase shift keying, and this is actually quite a popular solution. So this is something we can do only with digital modulation. I hope in the next slide it will actually be quite obvious what's happening with that type of modulation. And then what we can do, well, in the terms of digital modulation, we can have multiple layers of modulation. So basically, in the case of phase shift keying, we would have we can have a binary or quadrature PSK. So again, and the similar with the frequency shift keying. So okay, so I just go back to the slide in a moment, but this is actually what I wanted to show you here. So basically, those are different types of digital modulation. So over here, we can see this rapidly changing carrier signal, and it's described by this equation. Well, it's simply a sine function, right? And it's again conceptually, it's really quite simple. So as I mentioned earlier on, modulation is a way of altering any physical process, or any physical quantity in order to encode some information. So thinking about sine function, we have actually 3 parameters that we can modify here. So we have the A, which stands for the amplitude. And again, we can make the amplitude, larger, smaller, etc. That's what you've already saw in also with the analog modulation, right? And that would be one of the ASK or amplitude shift keying. Then when we get the sine, we can change the frequency. We can go higher. We can have 2 frequencies. The higher would stand for 0, the lower for 1. And that's what's called frequency shift keying. This is exactly what you see here, right? So over here for 0, we get lower frequency. Then 1, which stands for higher frequency, lower frequency, higher frequency, lower, and so on and so forth. Right? However, actually, when you think about the sinusoidal function in its full, there is basically one more parameter that you can control. And this is basically what's called the phase shift. Okay, because you can always, without even changing the frequency, so the frequency, right, is the change of the phase over time. But you can add a constant phase shift of your signal, of course, constant within certain symbol, within limited duration. That would simply, and changes of that kind of static phase shift can actually also, and they do, encode information, okay? And the advantage of using this phase shift is that it does not require the change of your frequency, okay? So it doesn't require you to use this wider bandwidth that I was talking about. You can still have sorry, somehow controlled phase, and the system would work. And this is basically what is described here. Possibly the phase modulation is the most challenging to visually describe, and you can see here it's not so nice with some chopped symbols, but actually it works, and actually you use it in your daily life even without knowing it, when you browse Wi-Fi and or things like that. Okay, so those are basically the three components. Okay, and okay, so yeah, going back to the slides, right? again, those are just the naming of those of different digital modulation techniques. So the amplitude shift keying, phase shift keying, when you just change the phase of the sine function, and frequency shift keying. Okay, and unlike with the analog modulation, when you need to accommodate for a continuous change, with digital modulation, you can have multiple levels or multiple layers. So you can have, let's say, low amplitude and high amplitude. Your low amplitude would encode 0. Your high amplitude would encode 1. And that's perfectly fine. You can live with that, right? However, what you can also do is you can have 4 different levels of your amplitude in the amplitude modulation. So level 1 would be, let's say, 0, 0. The next higher amplitude would be 0, 1. Next would be 1, 1, and 1 would be 1, 0. I'm explicitly using here gray code. That's for a bit different reasons. Okay, so basically you can have 4 different levels of amplitude where each level of amplitude allows you to control 2 bits. Okay, and then of course you can have 8 levels of amplitude, which allows you then to encode 3 bits and so on. You can actually match and multiply that. Okay. Similar case is with actually all other modulations. So you get the phase shift keying and the frequency shift keying. So in the case of phase shift keying, we can speak about binary PSK. So binary simply means you got 2 values of your phase. One stands for 0, one stands for 1. Okay, and this is basically positive and negative. So +1, -1. Okay. And again, that encodes you 1 bit. Then you can have a quadrature PSK, QPSK, which is 4 different phase components. So you would have, phase 0, 90 degree, 180 to 170 degree, and then again you can use that to encode 2 bits with single symbol at the same time. And of course, it can go up to 64, 128 different phases, and so on and so forth. And why would you do that? Can anybody think of a reason, or which one is?
I can't think of the type of noise that would destroy the signal.
Yes, actually, you're pointing into a good direction. So the noise might be is on one side of a problem here, right? But basically, okay. So just to put that in the order, in the perfect conditions, this goes to the principal armation area, right? So the more symbols you have, the more bits you can encode. And that, of course, means you can communicate faster, right? So a double or triple the speed as normally. However, as you correctly pointed out, and we're actually talking again a lot about that in the next slides, the more densely you pack your symbols, the more susceptible they are into your noise. Okay, because that means the same amount. So that basically means with the same amount of noise, if you have, let's say, just 2 amplitude levels, and you may have a noise which allows you to clearly distinguish between 2 levels. However, if you go to 8, you need much lower noise in order to still be able to distinguish between your signals. So that's the issue of resolution. That and this is indeed a trade-off that we'll be talking that in next slides. But that's actually a very good point with the noise. Okay. Another thing what we can do is, if we really want to further increase our speed, and that comes at a relatively low cost, we can do mix and match, right? So we know we can use amplitude for modulation. We know we can use phase for modulation, but from the equation, you know, the two are relatively independent from each other, right? So why actually not to use both in order to have, you know, double the amount of information, right? So we have one information encoded in the amplitude and the double that information encoded as phase, right? And this is something which is called QAM, so quadrature amplitude modulation, which simply combines both amplitude and phase in order to push more and more information. And then again, based on the number of levels, as I mentioned earlier, you can have a 60, 32, 64 QAM, and so on. Okay, so this is basically, sorry, any questions so far about the amplitude shift keying, phase shift keying?
So in phase shift keying, it's I expect signal, let's say 1 gigahertz, but what I received looks like it's shifted to 90 degrees. That means that it's this symbol and not that symbol, right?
Yes, exactly, right. So it's still, you know, 2 gigahertz, the same frequency, but you will observe this phase shift, right? So it will be seen as kind of, you know, jumps between the receiver. Okay, yeah, and okay, so typically what I want to talk in this slide is how it is done in practice, actually, because and that's one of the reasons why QAM modulation is definitely the most popular one, and well, it pretty much, you know, outperformed and expelled most of the other modulation type, is that it's actually, in terms of electronic equipment, super easy to generate. Okay, so just kind of speaking step by step. So this is actually one of the well, simplified version of what's called IQ modulator, and this is basically a device which, you know, allows you to transmit your translate your signal into the modulated signal. Okay, and the IQ is quite powerful because it allows you to cover and do any modulation which does not really require frequency shift. So basically, well, frequency modulations are a bit need some more complicated hardware. However, this would cover both any amplitude, any amplitude modulation, any phase modulation, any QAM modulation. It's basically the same architecture. Just, of course, you will fine-tune the precision. And this crosses that you can see here. Well, it's actually not a light bulb. So this is what is called a mixer. Okay, so basically, it's so mixer is like a device which combines two frequencies, which basically multiplies signals. So if you have one signal which is F0, or with the frequency F0, the other with frequency F1, at the output of the mixer, you will get a signal which gives you the sum of the two frequencies. So you have a higher frequency, F1 plus F2. Sorry, F0 plus F1. Okay. We'll basically talk about mixers also later on in the slide. So what's basically happening here is that you operate with two signals. One is your sine function, the other is a cosine function. Okay, and they're like 90-degree phase shifted with respect to each other. Okay, and over here with this mixer, your I signal and Q signal, those are just like some slow changing, basically DC voltage. So for the time being, how you can interpret those mixers is that they will, you know, it's a multiplication. So they basically multiply your F0, your carrier frequency, with a certain certain amplitude, right? And the reason why, when the signals are coherent, so you have the same source, just one is shifted by 90 degrees to form the cosine, and then you simply change the amplitude of your sine function and of your cosine function, and then you basically add them up together, and that's the signal that you go, well, for amplifier, filters, etc., to your antenna. Okay. So why is that important, and why is that actually useful? Is that this is relatively simple. Okay, it's not that simple in reality, but still relatively simple. That from the mathematical point of view, you should know that by combining different amplitudes of sine function and cosine function and adding them together, you can pretty much get any shape. So by any shape, I mean any amplitude and any phase shift of your output sine function. Okay, and that's given by the math. So for example, if you want to have a pure, okay, so pure sine function, that would be easy. Let's think a little bit about standard QPSK. Okay, when you had phase shift 0, 90, 180, and 270, each coding 2 bits of your signal. Okay, so in that case, the 0 phase shift would simply correspond to the row sine function, right? And then, so then, in that case, your modulation goes very simple. So the I component modulates your sine. So we put, just 1 on the I baseband input here, and the Q will be set to 0. So, at the output, you got just a sine function with the phase shift of 0, right? Now your simple change, you want to modulate, let's say 0, 1, which is 90-degree phase shift, which is cosine. Then of course the same story. You apply the Q, which is 1. I is set to 0, right? So at the end of the day, you got a cosine function, which again is pretty much 90-degree phase shift. So that's of course 2 trivial examples. Now, how could you get 45-degree phase shift? Any ideas? Okay, so basically, if you want to get the 45-degree phase shift of your signal, this is exactly halfway between the 0 of the sine function and 90-degree of the cosine function. So in that context, it's simply enough that you apply same amplitude 1 to both I and Q components, right? So you got sum of positive sine and sum of cosine. And when you add them together, you would actually get a sine, well, something between sine and cosine. So basically a sine with 45-degree phase shift. Okay, and that pretty much applies to all other, sorry, my throat is a bit dry, all other phase shift. Is this more or less clear so far?
I guess yes.
Okay, great. Now, so this is how the circuitry works, and the very convenient way of representing that signal is what's called IQ modulation plane. Okay, so typically the I and Q, that's the traditional name of in-phase component, which is used to modulate sine or to control amplitude of sine, which by amplitude, of course, you can also apply negative values to I, in which case you get a 180-degree phase shift. And then the quadrature component, that's the amplitude which modulates your cosine function. And with that, it's actually very convenient to represent your modulation or your symbols on a complex plane where I is considered as a real axis, whereas Q with quadrature component is considered as an on the imaginary axis. Okay, and this is the diagram you can see here. So basically, each of those points, if you check for IQ coordinates, that would correspond to the respective voltage or respective signal that you apply to the baseband, I and Q input. So for example, here you would, well, assuming, let's say that's some arbitrary voltage, 1 on I and 1 on Q, right? Here, to get this symbol, you will need voltage I of 1 and voltage Q of let's say 2 in again, some arbitrary units, right? So that's the way of visualization. And well, as you hopefully all know, apart from the real and imaginary representative, you can also represent your complex number in terms of amplitude and in terms of phase, right? And this is exactly something that would that you will see and that would happen for in here. So basically, when we speak about the amplitude, so this is the same amplitude as you would see in your modulation, right? So basically, by changing the amplitude, the distance of your symbol to the center of the coordinate system, this corresponds to changing of the amplitude of your sine function. Okay, and then when we go into phase, with, of course, for phase you always need some reference value. The phase would, on the other hand, correspond to the phase of the modulated signal. Okay, so in that case, you independently can control two different parameters in a classical QAM communication. So and the IQ component is really very, very convenient way of representing that modulation and that constellation. Are there any questions so far?
Yes, IQ have discrete states.
Yes, so it has, in this case, it has discrete states because it's it's digital modulation, right? So we are assuming we have always a digital signal over here. Mm-hmm. Yeah. Okay. So with that in mind, if you think, for example, about what you can see here, this would be called as a 16 QAM modulation. Okay, the reason being, you got 4x4, so 16 point, and the point, they both differ in both phase and the amplitude, right? That's quite clear. Now, what would you expect should look on IQ diagram phase modulation? Let's say 8 PSK with 8 different symbols, or 8 different phase values. Right? Or pretty much any phase modulation. What would you expect to see over here, or how would be the points organized or arranged?
Maybe on the circle?
Mm-hmm. Yes, exactly. They will form circle because, again, you're not changing your amplitude. So your amplitude is constant, and the only way you make your discrimination is by different phase, right? Whereas on the contrary, if we would have purely amplitude modulation, how that one would look like? So again, in terms of amplitude modulation, where again you have always the same phase, and you modulate your information using using only the amplitude. What shape would you expect over here? Let's say for 4 different amplitude levels. Okay, so right, so basically we know with that regard that your phase is constant. You're not changing anything with the phase, right? So there should be no change in the radial component, and only thing that changes should be different different amplitudes, right? So basically, that will be satisfied for a point which lie along a straight line from the center of your coordinate system, right? Because that's where, you know, they all have the same phase. We don't mess up with phase, but each of the amplitudes in your IQ diagram will correspond to stronger signal, to higher amplitude of your carrier frequency. Does that make sense? Hello?
I guess.
Okay, so okay. I think for the maybe next lecture, I would try to make some diagrams just to visualize what I mean. Okay, better. Well, the only important sorry.
I'm saying that would help us probably.
Mm-hmm. Yeah, I can imagine that's a bit abstract idea. Okay, so what's also important here to realize, but again, I will talk refine on some aspect of that later on, is that when you're using IQ modulation here, on the same, you know, you can squeeze much more points than just by using phase, and hopefully it's obvious, and if it's not, actually I hope it will be clear after the next week's lecture. Okay. Okay, so right. So for the moment that closes our block on the modulation. Again, I try to go back with some more drawings next week. Again,
Sorry?
yes. Go on.
If FM is better than AM, wouldn't something?
Sorry, once again, is FM or AM better? Is that the question?
Somebody just kicked me out, so thank you for that. Okay, so my question is, wouldn't something like be better?
Sorry, I couldn't hear a question. There are some glitches in the.
No, somebody just mute me, so I guess they don't want me to ask a question.
Okay.
Maybe I'll write it on the chat.
Okay, sure. Okay, I see your point. That's a good question. Okay, so when we speak typically about AM and FM, we are basically well, speaking about like analog modulation, right? The problem is that and then again, you know, FM is better or more robust to noise as compared to the to the amplitude modulation. The problem is that I don't think you can have, you know, efficient in order to use phase, you really need to use, you know, some discrete values. But the problem is that the frequency, this is, you know, effectively phase over time, right? So in that regard, I'm not aware of any system that would simultaneously use frequency and phase, simply because, you know, rapid change of phase can be also seen as shift of the frequency. So I don't think that would work on a practical basis, right? Simply because it's not that easy to, you know, interpret change in the phase or the frequency. And the second reason why frequency modulation is not really that much popular anymore is that, as mentioned earlier, you need to sweep through multiple frequencies. So in one way, it would increase the bandwidth of your signal, right? But also then in the other, it will pretty much significantly complicate your transmitter, because then you would need to have, rather than generating, you know, stable constant frequency from your local oscillator, you would, you know, need to change that frequency depending on the modulation, and getting that synchronized. Of course, it can be done, but it would, you know, increase the cost of the device. It would increase the the complexity. So basically, that's. I hope that answers your question. So as far as I know, I'm not aware of any modulation that will combine frequency and phase. Again, I think the main preventer is that frequency is the differentiation of phase in time, and then distinguishing those two parameters, which is much more complicated than between, you know, phase and amplitude. Does that answer your question?
Yeah, yes, thank you.
Okay, great. Okay. Okay. Leaving the quadrature and amplitude modulation behind us, I wanted to talk a little bit now about multiple access techniques. This is well, a bit unfortunate in the sense that this is another complicated topic. So, but okay, I would rephrase that maybe in 1 week time. So we know anyway how to modulate our information over center channel, how to, you know, encode that information into physical qualities. The problem comes that, you know, that most telecommunication systems, they are intended to serve more than single user, right? I mean, obviously there is no point of building, you know, base station network and mobile communication just for for one user. So that means pretty much that different users, different devices need to share the same resources. By resources, we mean either the same frequency or the same time. Okay, and well, hopefully you can intuitively understand that, you know, when you use two different signals at the same frequency and at the same time, they will, you know, overlap with each other. So that's not going to work, right? So you basically need different ways of separating your traffic or separating your communication. So yeah, so this is a little bit when you have like a multiple people, you know, shouting to each other in a crowded room. Okay, if you're standing next to that person, sure, you can get some information, but overall, you know, if they're on the other side of the room, all that signals will mix up, and you know, you cannot tell them what you wanted. Okay, and no different actually is with radio signals or with also wired signal, where multiple signals use actually the same wire. Okay, so how can we distinguish between the multiple users that share the same channel? And there are basically number of techniques. Three most common are time division multiple access, frequency division, and code division multiple access. Okay, so we will start from the first two, which are, well, basically the most common and most intuitive. But in general, there are many more. So what we can do, where we have two different axes here. One is the time, the other is frequency. And well, it should be quite clear, of course, that if you have a separation in time between two different signals, you know, they shouldn't overlap with each other. And also from the more advanced theory, you know that, you know, two signals at two different frequencies, assuming certain condition, can be also quite easily separated using filters. So typically when we speak about FDMA or frequency domain multiple access, we have a certain bandwidth which is allocated for our system, and we divide this bandwidth into subchannels, right? And then we allocate each subchannel to one user, so that, you know, they can be kept separately and not to interfere with each other. That sounds quite simple. A good example of that, or at least how it should work in theory, is Wi-Fi network. So you might see that Wi-Fi is has basically multiple frequency channels, and you can tune your router to a certain channel, which is kind of allocated to you for the whole duration of your communication. Well, in a perfect world, of course, in practical, you have no control, and you can have your neighbor choosing the same channel, but that's okay. But that's different stories. So the principle is each user is allocated their frequency for the whole duration of communication, and Wi-Fi is the most recognizable way of using that. However, you can do also different. So you can allocate the full bandwidth or certain bandwidth to one users, but chop up, provide each user with a time slot, so that you know, for a very short period of time, you know, the same frequencies by user 1, then by user 2, then by user 3, user 4, etc. And this is basically, on the other hand, how the GSM works. So the trick with GSM is, of course, that you want the time slots to be very, very short, you know, so that, of course, there's no delays, and that the users doesn't realize basically that any delay. So this is done in terms of a microseconds. Okay, but typically when your phone tries to make a connection with the base station, it will be allocated a time slot within which it is supposed to communicate and send the transmission. Okay, so yeah, and this basically to summarize the two aspects. So again, conceptually, it sounds quite simple. However, the devil sits somehow in the details, right? So if you think about the frequency FDMA or frequency division multiple access, you really need to make sure that your signal does not overlap anyhow with your neighbor's frequency neighbor's signal, and that leaves some additional bandwidth or frequencies that is basically considered a so-called guard band. Okay, so like basically a frequency domain no man's land. Simply because if you have a Doppler shift or if your device is a little bit off the intended frequency, you don't want to impact your users. Then in terms of TDMA, well, there are some, of course, similar issues with within time domain, right? So you would have a short period of to keep all your signals separated in time domain. However, another typical issue that that's coming with the TDMA, so time domain multiple access, it's also the synchronization, right? Because in principle, it's not very straightforward to make sure that your communication fits into the certain slot, because you may experience a certain delay simply because of the movement or because of the distance, right? So making sure that the transmitted communications falls into a designated time slot in a dynamic environment can be also quite challenging. But again, this can be done, right? And so FDMA and TDMA, that's the two basic multiple access techniques. As you can, of course, imagine, similarly to the different modulations, you can do mix and match, right? So you can, of course, divide both in terms of frequency and in terms of time. That's algorithms like frequency hopping, like well, partially sorry, no, not FDM, but basically the frequency hopping algorithms allow you to do, and that's actually implemented starting, I believe, from 4G, so fourth generation of mobile, or even actually 3.5 generation of mobile networks. Are there any questions here? Okay, or is somebody just being muted? Okay. All right. Okay. Give me a second, please. I think I should swap slides. Yeah, exactly. Okay. Right. So another technique, the third one from the basic mix, is called CDMA, so code division multiple access. This is a little bit more tricky. So basically, the CDMA or code allows us to transmit at the same time and same frequency, while still keeping different communications independent or distinguishable. And this is basically done by embedding what's called orthogonal codes into the communication. So here's our original data signal. And again, here it's XOR or mix with pseudo-random code. Okay, so what's important, the pseudo-random code needs to change much more frequently than the data. And then when we perform XOR, we have this signal, okay? And we have one core per communication. And this is the important principle here, that the codes of two or different communicating parties need to be orthogonal. And we're thinking here about orthogonality in mathematical sense. Okay. So, for example, those would be the 4 orthogonal codes, right? So we have, let's say, high pulse. Well, okay, let's call 1111, 1100, 1001, and so on. And well, when the two functions are orthogonal, it's basically when you cannot create those functions by simply superposition of each other, right? So basically, if you so for example, if you look at the last the fourth function, it cannot be created just by adding and subtracting the 3 previous ones. Okay, and same is true for the you know, all the other functions, right? So that's the mathematical definition of orthogonality. Now, another important aspect of orthogonality, and that again stems from the mathematical definition, is actually that if you multiply two orthogonal functions with each other, you get 0. And I hope this you know, should be kind of clear. I mean, you can see that in the you know, very basic vector operations. You know, two orthogonal vectors, if they're multiplied, they will always give you 0, right? And this is exactly the feature which is used to separate the traffic or information with different users. Because what's just happening is that on the receiver side, each receiver, of course, will be assigned a special code. And all they need to do is they take their own code, which is you know, intended for them, and they multiply received signal with that code. Okay, and basically what it will produce, well, what it will produce, well, basically it will create cancellation of all the signals with orthogonal codes other than the one which is intended for the user. Okay, so this is in that way the receiver can extract the signal intended for themselves while you know, getting rid or removing all of the communication intended for other receivers. Okay, and the most widely used example of this communication is actually the GSM or most of the GNSS signals. Okay, so basically, if you think about, well, okay, all except of GLONASS actually, but so if you think about the GPS signals, all satellites, they would transmit at the same frequency and at the same time, well, pretty much constantly, and still you can distinguish which signal was from certain satellite, simply because each satellite, they have assigned codes, right? And that's why you can figure out which codes from which satellite, and later on by pinpointing the time of arrival, you can calculate your location with respect to the GPS. Okay, is that more or less clear?
Yes.
Oh, all right. So okay. So one important thing with code division multiple access is that there is. You might think that okay, if CDMA is so efficient, right? Why we simply don't all use code division multiplexing, and then you know, we have the same bandwidth, same time, and we can serve multiple users. So that seems like a very efficient idea, right? The problem is in the multiplication of the pseudo-random noise. Okay, so as I mentioned, the pseudo-random noise needs to change faster than the digital signal you are discussing about. So this is actually the thing which would limit your capacity or limit your communication throughput. So without that, you could simply transmit your signal much faster, right? So again, there is always a trade-off and something for something. In terms of GSM, why this is actually a very good idea is because the amount of data that is being transmitted from satellite is actually very small, right? Because it's just basically something like an ID number and ping in general, because, well, okay. Just because you're not really interested in the data, you're interested in the timestamp for the position, right? So since the communication throughput is very slow, you can use the CDMA concept, and that's how it works. However, for more advanced communication like mobile or Wi-Fi, that is something that could really limit the communication capacity of your signal, of your communication. So okay, is that more or less clear, or are there any questions towards either CDMA or any of the issues that we have discussed? Okay, so there's no more questions. Well, again, if you want to ask something, there is my email that and IBS. Well, I will try to reply in a timely manner. And well, I think that was actually enough information for one day. So I think we can finish here, and I will prepare some more slides on the QMA modulation for the next week. And well, I'd like to thank you for your participation, and well, wish you a nice Friday and nice weekend. So thank you very much for attending.
Thank you.
Thank you. Bye.
Bye.
Thank you.